Okay, since we've been talking about vectors and sorting, the next thing we should talk about is searching. Okay, so searching an unsorted array or vector is pretty straightforward. Okay, so we have an array with, or a vector with n items in it, and if we want to search for an item, let's say we have this value x that we want to see. Well, is x in this collection? Well, the simplest thing to do is just start at the beginning here and check to see, well, is that the value x? Compare this with that. And maybe it is, maybe it isn't. If it isn't, we'll move to the next value and say, well, is that one equal to x? And is that one equal to x? Eventually, we might find one that is actually equal to x, and we can say, yeah, that item really is in this collection. Or the other thing that could happen is we could get all the way to the end. We will have searched all n items and found out that no, there's not a single copy of this value anywhere inside the array or vector. Okay, so basically every step of the way we check the element we're searching for with the next element in the collection. And then again, our goal is to find out either yes or no, is that value in the collection or not. Okay, so we could write a little function to do this. Right? We could have a search function that returns a true or a false. So true if the search value is inside the collection, and false otherwise. So what we can do is maybe assume that the search value is not going to be found. So we have a return value that we initialize to false. And then we could just simply go through all the elements in the vector. So starting at position 0, going up to vec.size, actually the value that's less than vec.size, 1 minus vec.size. And we can just check, is the search value, is the thing that got passed in up here, equal to the current value of the vector that we're moving through. And if that's ever true, we can change our ret value from false to true. And then at that point, it doesn't make sense to continue looking, so we can break out of the closest loop that we're in. And then one way or the other, we're going to return what's inside return value. So either we found what we were looking for, or if we got through all of here and this was never true, then retval would still have its initial value of false. Okay, so on average, if the vector has n elements in it, it would take about n over 2 iterations of the loop to find the element. Now, let me explain this n over 2. Sometimes we're going to get lucky, and x is going to be in the first half of the collection. But then there are going to be an equal number of times that we're going to be unlucky, and x is going to be in the collection, but it's in the second half. Okay. This evens out to about n over 2 iterations of that loop. So if there are 1,000,000 elements in the vector, on average it would take about 500,000 iterations of the loop to find out whether the search value is in the vector or not. Okay, so this type of searching has a name. We call this linear search. And that makes sense because we're just starting at the beginning and linearly looking one item at a time from the beginning to the end. Okay, so the question I hope to answer today is, well, if the elements in the vector are sorted, is there a better solution than just linear search? So let's think about how we use sorted collections in real life. For example, think about large paper phone books. In a city phone book, like in Chicago, for example, there might be 1,000,000 or more names in the phone book. Now, luckily, the names are sorted. If they were not, it would be much harder to use a phone book. Right? Imagine if we started on page 1 of the phone book to search for a name and we used the linear search approach. It would take us a week to find any phone number. So what we do, of course, we use the fact that phone books are sorted by last name to help us with the search. Okay, so let's talk about how we use a phone book. So large paper phone books look something like this. Okay, so how do we use them? Well, the first thing we do is we open the book somewhere in the middle. Okay, that's always the first step. And then we look at a name on that page, that sort of random page. Okay, so we find a name here. Now, if that name is what we're looking for, we're done. Now, of course, very, very rarely will this happen the first time that we open a phone book, but it's not impossible. Once we found the name, we have to indicate that this was a successful search, so we have to say yes or no. True or false. Okay, if the name we are looking for comes before the randomly selected name from the middle, then we know something about what's going to happen. So if the search name is in the phone book, we still don't know if that's true yet, but we know for sure it will not come after the selected name because the phone book is sorted. Okay, let me say that again. If the name we're looking for comes before the selected name, we know that the name that we're looking for is definitely not going to come after that selected name. Therefore, we shouldn't waste any time looking at the second half of the phone book. We can basically throw out half of the remaining names. Okay, so if I randomly kind of open this phone book and the name that was here was, I don't know, let's say Mahoney. Right, so that's this name here. And the name I'm looking for is Albertson. I don't know if Albertson is going to be in this phone book or not, but one thing I know for sure is if Albertson is in the phone book, it's not going to be over here, right? Because this name starts with an A, and the randomly selected name I chose here started with an M. So I know for sure that name can't be over there. So what I have to do now is kind of focus on this half of the phone book. Okay. So what if the search name, the name that we're looking for, comes after the selected name? Okay, so we know it's not a match, and we know it doesn't come before, so it must come after. So in this case, we know there's no point in searching the first half of the phone book. We can throw out the names in the first half and focus on the names in the second half. Okay, again, if the name was Mahoney that I was looking for, and I'm sorry, if the name that I was looking for was Peterson, okay, and I randomly opened the phone book and saw the name Mahoney, well, I know Peterson's not going to be in this half, right? I can throw out this half and focus just on the second half. Okay, and we kind of intrinsically know how this works. I doubt anyone ever explicitly taught us how to use a phone book like this, but this is what makes using a phone book so easy for us. Okay, is that this repeated throwing out of half of the remaining names. Okay, so we do this over and over again. Okay, and this is the basis for this algorithm called binary search. At each repetition, we're eliminating half of the remaining names. Because we're not bothering to check half of the remaining pages. Okay, so now the question is, well, how many times will we need to search a sorted phone book with 1 million names in it to find one value? The key here is to remember that we're throwing out half of the remaining names each time we figure out that the name that we found is not the one that we're looking for. Okay, well, we start with 1 million names, but then we open the book, and if we don't get lucky, we know we can throw out one half of the phone book, and now we're left with 500,000 names. And then we're going to open that chunk in the middle, pick a name, and maybe we get lucky, maybe we don't, but chances are we're going to throw out another half of those remaining names, and so on and so on. Here are my numbers, I'm just approximating. Okay. But it looks like it only takes about 20 times that we have to do that. Open the phone book in the middle, pick a name on that page, and see if we get lucky. If we do it 20 times, we know for sure we're either going to find the name or we're going to know for sure that the name is not in the phone book. Okay, so in other words, how many times can we cut a 1 million name phone book in half before there are no more names to search? Well, turns out that number is 20. And there's a name for this type of question. It's called a logarithm. Okay, so whenever we talk about a logarithm, we're saying, 2 to what power is equal to a million? The way we write that as a logarithm is we say log base 2 of a million is equal to 20. So in order to search a phone book with 1 million names in it, it would require that we look at most 20 names before either we find the name we're looking for or know for sure that the name is not in the phone book. So now imagine we had a worldwide phone book with maybe 1 billion names in it. And now the question is, well, how many names would we have to look at in order to find someone in this 1 billion name phone book? Okay, and it turns out the logarithm, the base 2 logarithm of 1 billion, is actually only 30. So the difference between a million and 1 billion, there are 1,000 millions in 1 billion. So we got 1,000 times larger phone book, but we only had to search 10 more names. Okay, or go through that process 10 more times. So I'm sure if we had an actual 1 billion name phone book, it would still be pretty easy for any one of us to look up any person's name in the world. Okay, it would only add on about 10 iterations of that algorithm. Okay, so this is kind of interesting. Let's compare these two algorithms. If we wanted to search 1 billion names, binary search would take about 30 comparisons of names. And what I mean by this is opening the book kind of in the middle and comparing the first name on the first page or the left-hand page with, is that the person that I'm trying to contact? If we did a linear search, it would take about 500 million comparisons. Again, that n over 2. Sometimes we get lucky, sometimes we get unlucky. It averages out to about n over 2 comparisons. This is a tremendous difference in the amount of work required to do the search. So the repeated cutting in half of the remaining items, that's called a binary search. Okay, so the question now is, well, how do we implement binary search in C++? Well, the first thing to understand is that this algorithm only works if the items are in order. If you have a collection of items that are not in order, well, you can't use binary search. Your best approach is just to use the plain old linear search. But if the items are in order, you can use binary search. And the first step is to find a value in the middle of the collection. So remember, in the phone book, you just kind of randomly open the book in the middle and search for a name. Well, now all of our data is going to be in a vector. So since we know the items are in a vector and the elements are read using an index value, we need to choose a number, an index, for that middle value. Okay, so we know the first element of any vector is always at position 0, and the last valid index in any vector would be the sorted vector.size minus 1. Okay. So this is kind of always true. If you want to find the last item in a vector, just take the size minus 1. That's the index of the very last element. And the question is, well, how do we find the middle value? Well, using the index values of the first and the last element in the vector should allow us to find us a value in the middle. Okay, so it turns out if we take start plus end, we sum those together first, and then divide by 2, okay, that should give us a value in the middle. So let's imagine we had a relatively small vector with maybe 30 items in it. Okay, if we had a vector with 30 items in it, the start would be 0 and the end would be 29. So we can do a little bit of math here. We can sum those together first. 0 plus 29 is 29. And then divide that by 2, and we get 14. 14 is about in the middle of the vector. Okay, remember, this is integer arithmetic, and the any fractional part gets truncated. Okay, remember, though, that the start and end are going to move around, because we may throw the first half of the remaining items out in one iteration, and then throw out the second half in the next iteration. So it is possible for the start to be, say, 10, and the end to be 20. Okay. We know the number between 10 and 20, probably without thinking even, is 15. Luckily, our arithmetic expression is still going to work. So we could take our start and end. 10 plus 20 is 30. Divide that by 2, and we get 15. Okay, so that's a good way to find the value in between any two numbers. Let's just sum them together and divide by 2. Next, we have to compare the search value with what's in the middle. Okay, so that's going to look something like this. This is similar to how we searched in linear search. We basically pass in a value, and then we have the sorted vector, and now we have a middle number. We could say, are these two things equal? And if so, just like in linear search, we could set our return value to true, and eventually this is going to be in a loop where we can basically stop looking. Now, if we didn't get lucky, and we actually have to decide which half to throw out, well, that code's going to look something like this. Okay. So again, we're kind of searching, do we get lucky? Is this what we're looking for? If not, the next thing we do is we say, is the search value less than what's in the middle? Okay, or does the search value come before the middle item? Okay, so think about this. This was the Albertson example. Does Albertson come before Mahoney? Well, yes, that's true. So the way we can kind of simulate throwing out half of the remaining items is just to change the end value. Instead of being at the far end of the vector, we could take the middle value minus 1. We know for sure it's not the middle. We've already checked that. So middle minus 1 is the next kind of largest one that we should check. And we set the end equal to be that value. Now, if the search value is not in the middle and the search value is not less than what's in the middle, well, then the search value must come after the middle value. We don't even need an if in this part. Okay, so this is the Peterson example. Peterson comes after Mahoney, so we could change start to be middle plus 1. Again, middle plus 1 is kind of the minimum value of where we should search. Okay. So now we have to think, well, how are we going to repeat this code? So all loops must have a condition that will cause the loop to stop executing. On each iteration where the search item is not found, the start and end are actually getting closer and closer. Okay, this is because when we do change the start value is getting larger. And when we do change the end value is always getting smaller. So the start and end, when they're moving, they're getting closer and closer to each other. We will know the item that we're looking for is not present if the start index value ever exceeds the ending index value. Okay. So, start and end are moving closer and closer together. If start ever becomes greater than the end, well, we've kind of moved the start and end so close together. We know for sure what we're looking for is not in the collection. Okay, then now what we're going to do is we're just going to move that calculation of the middle. We're going to move it inside the loop here. So every iteration of this loop, we want to get a new middle value, which we can, again, using this little bit of arithmetic, we can find the middle value. Okay, of course, all of this code should be in a function. Right, so we could do something like this. We could have a binary search function that returns true or false. Again, we'd want to pass in a sorted vector by reference, and the value that we're searching for. Okay, and if you put all those pieces together, you should have enough to create a binary search, or what I sometimes call it a phone book search.